you have fluid flow, say in a pipe, and say for example in this case, say the ambient is colder and the fluid that's flowing in there is hot. So that fluid temperature over here I call it Ti. I stands for inlet. So Ti is greater than T infinity. And because of that, heat is going to travel radially outward. It's going to transfer outward. And what happens is that it's going to exit at the end of the pipe with a temperature that I call Te. So, could you make a guess if Te, this temperature over here, is it higher or lower than Ti? Right, it should be lower. That's because as this fluid flows along, it's going to lose its heat to the environment. And as it loses heat, its temperature is going to drop along the way. So Te will be at a lower temperature. Now, if I want to find out what is the so-called average temperature in between, what I'll do is to take this, what we call the bulk fluid temperature, Tb. So, the bulk fluid temperature. Tb will be equal to taking your Te minus Ti divided by 2. So, the average temperature in between those two. So it's kind of like over here, and you can call that as a Tg temperature, kind of like a car temperature average one inside. So the heat that's transferring out, because there's flow inside this pipe, so there's convection that's happening across over here, like this, close to the surface. So there's a certain amount of convection. And because there's convection, you'll be governed by your convection heat transfer coefficient H. So we know that the heat would get transferred out as it flows along. And if this is flowing at a certain mass flow rate, and this surface area, the cross-section area of the pipe, this area, let's say I call it cross-section AC, cross-sectional area. Now, the heat lost would be Q equal to mass flow rate multiplied by specific heat capacity of the fluid. So there's a certain specific heat capacity of the fluid. And multiplied by the temperature difference. So because this part here is higher, at a higher temperature than Te, so Ti minus Te. So that is the setup for the heat loss, right? And you have seen before that this term over here, m dot Cp, and this C here refers to the small letter c. All right, I can't write it any more smaller. If it's any more smaller, you couldn't see it. It's a small letter C, but I can write a capital letter C. That's not by writing it bigger. That's writing it using this symbol, or this kind of like my version of capital letters, so that you can see capital letters. Because it's not about the size. So this could be represented, is equated similarly in a same way. Okay. And there are words behind all these symbols. So you would need to know how do we call them in English. This term here, m dot, that is your mass flow rate. And the unit for mass flow rate is kilograms per second. That term C, small cp, that term over there. That is called your specific heat capacity. And just in case you're wondering, these are just word symbols, but engineering, the engineering sense, the engineering meaning is what does it mean? If I were to write a unit, this is kilojoules per kilogram degree Celsius. This sort of unit will tell you something. It tells you certain fluid property over here, that this fluid or this material, in order to increase the temperature by 1 degree Celsius for 1 kilogram of that material, how much of that energy do I need? That is the meaning of specific heat capacity. So you could have water. I already know water, the specific heat capacity of water is actually 4.18 kilojoules per kilogram degree Celsius. What that means is that in order to increase 1 degree Celsius of the temperature of the water by 1 degree Celsius for 1 kilogram mass, I need 4.18 kilojoules of energy. That's a lot. So these two terms in combination will give you this capital letter C. And capital letter C is what we call the heat capacity. And heat capacity would have the units of kilowatts per degree Celsius. And what it means, again, is that for this material, if I want to increase 1 degree Celsius, that is the amount of work or the power that I need to put into that material, right? Power, in this case, maybe electrical power in order to supply, in order to increase that material by 1 degree Celsius, you need to supply that much power. And power has a unit of watts, or in this case, I'm putting it as kilowatts. So that's the meaning of the heat capacity, mass flow rate, and specific heat. I would need you to recall this as we move along in the following slides. We're going to start by having a quick revision of how did we end up on this slide over here. Before we were talking about this slide, if you look up over there, we had a few other things that were going on. And particularly before this deck of slides, you have seen how we went about trying to derive LMT, lock-mean temperature difference. You could only solve for LMT, lock-mean temperature difference, if you have all the inlet and outlet temperatures. Only that. Only then can you solve that. Because LMTD, the equation itself, requires all your hot inlet and outlet temperatures and the inlet and outlet temperatures of the cold fluid. All of them. 4 numbers. If you don't have any 2 of them, you would use what we will be seeing later, the effectiveness NTU method. If you don't have only 1 of them, you've got 3 of them, some inlet, well, there must be 1 pair of inlet outlet and another inlet or outlet. So 3 no ones. It's possible that you could solve using LMTD by finding out the 3rd, actually the 4th unknown temperature. So in some of your tutorial, you get to practice that one. But let's have a look if we don't have 2 temperatures. What is this so-called effectiveness LMTD method? Sorry, effectiveness NTU method. So effectiveness will introduce a new symbol, epsilon. And epsilon is the symbol that you often get to see, epsilon dash NTU method in some of the textbooks. Sometimes they only call it effectiveness method, sometimes they call it NTU method, sometimes effectiveness NTU method. The textbook, they call it differently. So I want to start by introducing the effectiveness. What does it mean? Effectiveness is a ratio that we use to measure the heat exchanger. And what is it that we're measuring? We're measuring the actual heat transfer against the maximum possible heat transfer. Now, if you take a step back and have a look, it is kind of like makes sense here. Your heat exchanger would have the maximum possible heat transfer. And heat exchanger isn't all about exchanging heat. When you have a hot fluid, they'll exchange heat with a cold fluid. And I'm saying exchange because it might be the cold side that you're interested to gain heat. You might be interested in that. Or it might be that you're interested to lose heat over at the hot fluid side. But either side, there'll be heat that's going to be exchanged. But when we talk about heat transfer, then heat can only transfer from hotter fluid to the cooler fluid. Okay. So if I have a heat exchanger and if it's not doing its peak performance, that is the maximum possible heat transfer, then I can take this ratio. If it's not doing the maximum, then how much? Take that how much? Divide by its maximum. That I call it the effectiveness of the heat exchanger. Okay. And the symbol for that is Q divided by Qmax. So Qmax you have already seen in the previous lecture. In the previous lecture over here, this is the definition for Qmax. So if I have a quick revision with you, this Qmax is equal to the C mean, and this C was the capital C that I had before, the heat capacity. Okay, the minimum of the heat capacity. Why minimum? Because you have two fluids. These two fluids will be flowing against each other or together with each other in the heat exchanger. And these two fluids would have its respective mass flow rate, m dot, and respective specific heat capacity, Cp. So if you multiply the mass flow rate and specific heat capacity of each fluid, there will be one number that will be higher than the other number. The number that's lower is what we call the capital C min. Later on, there will be an example to show you that. So we often talk about C min. If you're wondering what is that minimum thing, is that minimum heat capacity of one of these fluids. How do I know which one is minimum? You got to take the mass flow rate multiplied by the specific heat capacity. So that is your C min. And the other term that you can see over there, the difference in the temperature, and I want you to have a close look at the difference in temperature. That's THI minus TCI. The hot water inlet and the cold water inlet. These two numbers must be the largest temperature difference in your entire heat exchanger. Why is that so? Because your THI, which is your hot fluid is coming in, must be the hottest in the entire heat exchanger. And the cold fluid is supposed to flow in to cool down this hot fluid. That cold fluid must be the coldest in your heat exchanger. So these two inlets, hot and cold, would represent the largest temperature difference in your heat exchanger. Take that largest temperature difference, multiplied by C min, you get your Qmax. That is your maximum possible heat transfer. Right. So that is your Qmax. So Qmax will be this Qmax, same as this Qmax over here. So if you take the actual heat transfer divided by Qmax, the maximum possible heat transfer, that will give you the effectiveness. I want to have a closer look at this following term as well. So if you look at these words over here, from the energy balance, we can substitute Q and Qmax by temperature difference and heat capacity. And there are two forms over here. This first form over here refers to, in this case, if C min is equal to CH. Now, sometimes I pronounce capital letter C as just C. Sometimes I pronounce small c as just C as well. So look out when I write it. It's C, capital or small letter. So in this case, C min equal to CH. That is, if this is a condition. Then we look at this effectiveness, which is the actual heat transfer divided by the maximum possible heat transfer. Now this maximum possible heat transfer is what we have seen already, right? That is your Qmax. This part over here refers to when we are looking at the hot fluid flow. How do I know that? Because I could see that this is CH. That refers to the heat capacity of the hot fluid. And the temperature difference between the hot fluid inlet and the outlet. So that numerator refers to the actual heat transfer for the hot fluid. Take that ratio, you can get the effectiveness. Now, if C min is equal to CH, that means these two terms could cancel out. And what you're going to get will be THI minus TH naught divided by THI minus TCI. You only look at this set of effectiveness equation if your C min is your CH. If your C min is not CH, because C min could happen on either side. How is that so? That's because when you multiply the mass flow rate by its specific heat capacity of these two hot and cold fluid, only then could you figure out which one is your minimum. And the minimum one would be either your hot fluid or your cold fluid. It depends on the numbers that are given to you. And later on, there will be an example which will be that. So if you have a case where C min is your cold fluid, CC. If that's the case, that means that numerator over here would be your cold fluid heat capacity, CC, multiplied by the temperature difference between your cold fluid, that is your outlet and your inlet, TC naught minus TC inlet. And if C min is equal to CC, that means these two terms could cancel off, leaving you with TC naught minus TCI divided by THI minus TCI. So you can only use one of these. You cannot use two of these because you can only have a minimum of either your hot fluid or your cold fluid. You cannot have two as a minimum. Because there will be one number that's larger than the other. So in that case, if it's your hot fluid that has a C min, then you'll be using this set of effectiveness equation. If it's your cold fluid that has the minimum value compared to the hot fluid, then you'll be using this set of effectiveness equation. Not to worry, there will be two examples to show you how do we actually make use of that. Your effectiveness number is actually a dimensionless number. Something tells us that it must be between 0 to 1, because you're comparing against the maximum possible heat transfer. So If it's indeed at its maximum possible heat transfer, you get effectiveness equal to 1. Normally, most of the heat exchanger, you wouldn't get equal to 1. You get it close enough. Later on, we'll see what is that close enough number. You'll be 0 point something, right? Effectiveness number. So please, as you solve your question, if you get an effective number that's 1.2, come to me. I think you got an extremely effective heat exchanger that's higher than the maximum possible heat transfer. I want to talk to you. But most of the time, it's less than 1. Now, if you get a negative epsilon, if your effectiveness is negative, I also want to talk to you. So I could readjust this formula. Now, could you insert this word over here, just right over here? If effectiveness PHI, TCI are known, then the actual heat transfer can be readily determined from the following expression. This expression over here, and actually this expression is not a big deal. This one is just Q equal to epsilon Q max, right? Where it's coming from here, right? So this is just another way of writing the same thing. So there are some governing equations behind this effectiveness. And I'm going to slide over here. This is something that's not included in your lecture material, but not to worry, because your seniors actually did calculations based on finding out what's the epsilon using the NTU, which is number of transfer units. I haven't introduced that to you yet. It's coming shortly. And this is CR over here. So what they did is to substitute that into the following formula in order to figure that out. These tables, they are not in your lecture notes. I see that this year, the Glasgow decided not to have you do the calculation, but to look at graphs and do that, look at the graph and do that interpolation to find out what is the value of effectiveness. And I'll walk you through how to do that. So I'm going to touch back on this set of equations later on, but just to briefly introduce to you, there are those parallel flow, counter flow, shell, and tube, one shell pass, n shell passes, cross flow, all heat exchanger. There are just so many different configurations with different sets of epsilon and NTU relationship. There's just C, capital CR that I haven't introduced yet shortly. So I'm going to come back to this table again. But now, as what you have seen in that set of equations, if I were to plot this set of equations over here, say for example parallel flow. Now this is epsilon. I'm going to sketch in terms of the axis of epsilon, effectiveness, and the x-axis as NTU, number of transfer units. I haven't introduced you that yet. If I look at just this equation as a mathematical formula, axis y is epsilon, axis x is NTU. These are variables. So the kind of graph that you'll get will be something that looks like that, arcing up, of which depending on my CR value, I will get different sets of lines over here. Different sets of lines. different sets of lines over here that decides what is that capital CR. So it is actually this kind of graph that we'll be dealing with. You could see that effectiveness is a function of NTU, and this CR here is actually equal to C min divided by C max. And CR is actually called your heat capacity rate. No rate, ratio. Heat capacity ratio. So you heard it already. This capital letter C is called heat capacity. Capital letter C with a small subscript R, we call it heat capacity ratio. Ratio. Is there a dimension for it? C min divided by C max. That's equal to CR. Is there a dimension? It's dimensionless. So your CR is actually a dimensionless number. In certain textbooks, they actually do away with the small letter subscript R and just write capital letter C. So as you look into various different textbooks, just be aware that this is written differently by different authors. But over here, I could see that the textbook that Glasgow is using, that one has capital letter C and subscript R over there. So these are the equations behind it, right? The equations behind, these are the equations behind all these graphs. And later on, you get to see these whole sets of different graphs that we'll be using today. So as I was saying just now about C min and C max, we wouldn't know if the hot fluid or the cold fluid would be C min. And if one of them is C min, the other one gonna be C max. That's the way it works. In order to figure out which one is C min, we're gonna take the max flow rate, m dot, multiplied by the specific capacity, Cp. Multiply that out, you get a number for the hot fluid. Do the same for the cold fluid and then compare them. The smaller one will be your C min, and the other one will be your C max. Take that ratio, that gives you your heat capacity ratio. So you could see that's what it's trying to say over here. It can be equal to this or equal to this, depending on if your hot fluid or cold fluid has the maximum or minimum size. Later on there will be an example to show you that. The NTU is not a university. It's number of transfer unit in this module. Is what sort of number of transfer unit does that mean? Actually, NTU is equal to capital letter U, A, divided by C min. We would have we would have seen C min before, right? And this U over here refers to your overall heat transfer coefficient. And it has the units of watts per meter squared Kelvin or degree Celsius. That's your overall heat transfer coefficient. And area over here just refers to your surface area where heat transfers perpendicularly. So over here it says that it's possible to develop the analytical relationships between your epsilon, your C min divided by C max, and NTU, and that's why I inserted this table over here. This is your analytical equation. What does it mean by analytical equation? It means that you could find out exactly what is the value of effectiveness if you are given NTU and CR. That's your analytical means you can find things very accurately. So in practice, we only use, last year they used these equations here, but this year I noticed that they are moving away from that. You'll be using instead this set of graphs. That's more fun, right? It's actually easier. Out of easiness that you get, you also will get a certain error, margin of error. So I'll tell you why that happens. So here are two graphs, or two slides with graphs. These two. I'll walk you through. This first one is talking about when you have parallel flow. All the axis over here is epsilon versus NTU. Okay. Oh, by the way, your NTU formula up here will not be provided by XN. It is kind of easy. Anyone could say that NTU is equal to UA over CE, so you must be able to do that too. So this is one such plot for effectiveness versus NTU. You have effectiveness versus NTU plot for counterflow. So actually the test over here is the test you can use to look at the correct graph given question set as NTU. So you must be able to read the question and understand, wow, this is actually a counterflow. So go to this graph and figure it out. If you have a question that says that this is a shell and tube, and some textbook actually put shell dash and dash tube, shell and tube, heat exchanger. You will have seen that as well. But in this case, this graph over here refers to one shell and only one shell, and any multiple of two tube passes. So you can see here, there's only one shell and multiple of two tube passes. So there are two over here. The next set is going to look like this. 1, 2, 3, 4. Okay, and you have your in and out of the shell. So that is the graph for one shell, multiple of two tube passes. If you go to the next slide, you got to see two shell passes and any multiple of 4 tube passes. So you have two shells over here and count the number of passes. 1, 2, 3, 4. Okay. You could use this graph if you have the case of two shells and only two shells. And multiples of 2, 1, 2, 3, 4. 1, 2, 3, 4. Okay. This is in, and this is connected, and this is out. Okay. There are two more. One of them would be cross flow over here. So whenever you have cross flow, you have to ask yourself this question. Is it a case of ice plus Milo? Remember that? If you add ice to Milo and stir it together, what do you get? Ice Milo. Is that a heat exchanger? It's not, because it's all mixed together. Why is it that when they are mixed together, ice Milo, that it cannot be a heat exchanger? Because a heat exchanger, while we were saying that, yeah, it comes together, it exchanges heat. We actually want to recover that fluid for circulation. So once it's mixed together, you can't really recover that hot and cold fluid for recirculation. Once ice Milo is mixed together, can you extract ice anymore? You cannot. So that's not a heat exchanger. So when you have cross flow, you need to ask yourself the following question. There'll be one fluid that's flowing in, it may be hot or it may be cold, and the other fluid that's cross-flowing through it. This fluid that's cross-flowing through it, would it be mixing or not mixing? Right? So it could be either side here. They are cross-flowing each other. So if you have these two fluids, they are not mixing with each other, and within itself, it's also not mixing. And you call this as both are mixed. How does it look like? If I have one side that's flowing through, and I break it down into several tubes flow. So this big tube here that's coming in and it gets distributed to smaller ones. So within that smaller ones, you could simply say between the individual tubes, they are not mixing with each other. So this flow here is not mixed. I have a cross flow that's coming in. If I just open this to ambient air and fan it, this fanning it through these various tubes, the fanning cooler fluid is going to be mixing with each other as it flows through these smaller tubes. This one will be mixed. So one unmixed and one mixed, which is this case, one fluid mixed and the other unmixed. If you want two of them are mixed, what I need to do is to kind of like partition it. Partition it in this way. There will be tubes, and then I kind of put a plate with holes on it so that the tubes can go through. Partition it. And put it under this fan wing. So you can see that the fluid that's going past these tubes that is partitioned, this fluid is not mixed. Neither is the one that's flowing through the tubes. So this is not mixed. This one that's flowing through it is not mixed. It's not mixed adjacently, yeah? But it's sort of like mixed top and down, right? Because it's partition wall. But this sort of configuration, we call it unmixed. So your cross-flow heat exchanger can only have two types. One is one mixed, one unmixed. The other one is both mixed. Sorry, both unmixed. So you cannot have both mixed here because of the ice-minor story. So symbolically, it's written. I'm not sure, could you see it? Maybe I'll just increase it. You can see this grid to represent both are mixed. And you see over here, there's no grid because one is mixed and the other one is unmixed. Okay. So for any one of these, you will get the following corresponding curves. That is again with the axis of epsilon versus NTU, epsilon versus NTU. Particularly when you get to the cross flow, that has one fluid mixed and one fluid unmixed. There's another further division in between that. This division says that, okay, the one that is mixed, is it the C mean or is it the C max? So there's a further distinction. Look at it, read the question. Cross flow, I can see that. Read it further, it says that one fluid is mixed, the other one is unmixed. And look at it further, the one that's mixed, is it C mean or C max? If it's C mean, then you'll be using the solid line of this graph. If it's C max, you'll be using the dotted line of this graph. One popular mistake is that students thought that because each of these lines represent your C mean divided by C max, so you really need to calculate that number. And this number is increasing in this direction. Could you see the labeling? It's increasing in this direction. Alright. But it's labeled in the other direction. So some students make this mistake. Be careful about that. It's the same for all of this. Your C mean divided by C max is increasing in this direction. This is the slides that are provided in the lecture notes, but in your exam data booklet, you get a black and white view. That's what you get. Again, I'll walk you through very briefly. Although these equations are provided, and you could either choose to do what your senior did, that is to calculate the C value, the NTU, and NTU over here, sometimes in certain textbooks is represented by the letter N only. So this is also the letter for NTU. Okay. So maybe I put it up here. N. So this one here is for parallel flow, this counter flow, shower and tube that we have seen before, one shell pass, no pictures in, and then 2, 4, 6 tube passes. If you have cross flow, this for both are mixed. If you have cross flow again, if one stream is mixed, which one is the mixed one? Is it the C min or C max? In this case, this M over here, I think it's just a typing error. So I'll be highlighting to the class about that. So you got to see which one is your maximum and which one is your C min. And that refers to your mixed fluid. So let's have a look at an example so that you have a good idea. You have this heat exchanger. It's given to you as a sketch, but actually in an exam, normally you don't get this kind of figure. You just read that English words and try to understand that. So it says that hot exhaust gases which enter a thin tube cross flow, look at that, cross flow, heat exchanger. And the interesting thing is that we've never seen this before, thin tube. So what does thin tube means? It just means this. Okay. I'm not sure, could you sketch it out, but you kind of know that English. Thin tube. It's gonna be that. Okay. So, if you can't visualize, no problem. It wouldn't hurt you either. So there are those conditions that are given. So I'm going to just fill in using this figure over here. There are those conditions that are labeled, that will be used to label the following figure. Your THI is given to you in the question as 300 degrees Celsius. And you got to know which one is your hot fluid and which one is your cold fluid. In this case, read the question. It says that the hot fluid side, what kind of fluid is that? It's actually your hot exhaust gases. So it starts to go into the heat exchanger at 300 degrees Celsius and exits at a temperature that's 100 degrees Celsius. That's for the hot side. And over here, in the question, it didn't really say both mixed or unmixed here, if you look at it, but this is the only indication over here. So if you were to get a question, normally this would be stated. It is mixed, unmixed, one mixed, one unmixed, both unmixed. So on the cold fluid side, it says that the fluid that's going in is water, has a mass flow rate of 1 kilogram per second. It enters at a temperature of 35 degrees Celsius and exits at a temperature of 125 degrees Celsius. So sometimes it's good to develop that engineering sense. Take a step back and look at it. Are those temperature numbers reasonable? If this one were to exit at a temperature that's 500 degrees Celsius, tell yourself, hey, something is not right and it can't be. This one cannot be exiting at a temperature that's higher than 300 degrees Celsius. No way. Right? So those are the parameters that are given. You are also given for the heat exchanger, UH, which is your overall heat transfer coefficient, is at 100 watts per meter square Kelvin. And you're asked to find out what is your surface, the surface area for the hot fluid. You're asked to find it out. Now, what is interesting is that I'm not sure, have you noticed this graph here that's right beside the figure? Some of you may be wondering, I know how a parallel flow heat exchanger temperature graph is going to look like. In fact, it's going to look like that. That's for parallel flow, right? You've seen it before. That's for a parallel flow heat exchanger. The graph must look like that. For a counterflow heat exchanger, you've seen it before as well. It looks something like that. Counterflow, the arrow indicates the direction of the flow. So you have seen for power flow and counterflow, but how does this temperature versus length of heat exchanger graph looks like for cross flow? Can't imagine. Sort of blows your mind. For cases that are not parallel flow, for cross flow heat exchanger, the flow temperature profile, meaning this Tx profile, is as if it were counterflow. So that's the one that we kind of like standardize on. For cross flow is neither parallel nor counter flow, but the way that we are going to do is to sketch it as if it is a counter flow heat exchanger. That is for cross flow. Right? So that's why you could see this graph over here. It looks very similar to a cross flow heat exchanger. There is one sentence that's missing in your question. The sentence is over here. The exhaust gas specific heat is approximately 1,000 joules per kilogram Kelvin. So that's good. Let's see how can we solve this question. I leave kind of like one slide empty, is it, in your notes? One slide empty so that you could write down the following solution. The setup solution is about about 10 lines, so we kind of like adjust. Because I've seen before that student kind of like cram everything, just 10 lines over here. Well, that's easy. So just give yourself some space. So we're going to start by looking at the property table, the fluid property table. And over in Holman, you'll be referring to 8, 9 table, for the water table. We're here to look at Holman. And we know that we always need to find out the film temperature. So we'll be taking for the cold fluid. This is the average temperature for the cold fluid, and that one is 35 plus 125 divided by 2, you get 80 degrees Celsius. Using 80 degrees Celsius, you're able to figure out what is the specific heat capacity of the cold fluid. It is 4197. If you use Holman, you need to do a little bit of interpolation. Okay. If needed, you'll be provided those kind of tables, property tables. So you just need to know how to go about doing interpolation. And you need to do interpolation so well that it takes you a very short amount of time to do it. Because you can't spend all the time in doing interpolation. By the way, your exam is only 1.5 hours. 4 questions. Right. So you could see you need to be so good. And I know you are very good. So there's one property that's not included here, exhaust gases. That has a CPH is equal to 1,000 joules per kilogram Kelvin. That's the one that's given in the question, but it wasn't written in. So as I was saying, we need to figure out which one has got the maximum and which one has got the minimum. So let me have a look. CC for the cold fluid. That will be M dot C, C, P, C. That will be equal to 1 kilograms per second multiplied by 4197. Now if you use Holman textbook, you get a slightly different specific heat capacity value. So over here I'm just adopting the materials that was given by last week. So you get 14197 watt per Kelvin. So we need to find out what is your CH in order to say which one is higher and which one is lower. We know that we could find out CH by saying that your QH must be equal to your QC. Now how is this possible? The heat transfer rate for the hot fluid, if you think about it in a whole heat exchanger, it's got to be equal to the heat transfer rate for the cold fluid. What that means is that if your hot fluid is flowing, you will lose heat. This losing of heat must be whatever heat is gained by the cold fluid. It must be provided that we insulate the entire system. So that heat that's transferred over, it must be equal to each other. So that's why your QH can be equal to your QC, of which your QH would be CH, and the temperature difference, THI minus TH0, equal to CC, TC0 minus TCI. So we could re-express this whole thing with CH as the subject, CC, TC0 minus TCI, divided by THI minus TH0. And then we could substitute all those values inside. You have your CC as 4197 multiplied by 125 minus 35 divided by 300 minus 100. Solve that one, you will get that equal to 1889 watts per Kelvin. So here comes the important part. You have your CH and your CC. That is when you need to decide which one is smaller and which one is larger. So is it CH or CC that's smaller? CH. So you say that this is equal to your C min. And if this is equal to your C min, the other one will be your C max. Okay. So what we need to do next is to find out the effectiveness. And the effectiveness, as we know, that is equal to Q over Q max. And later on, I'll try to make use of this. But for now, what I need to do is to find out what is Q max first. So Q max, as what we have seen before, is equal to C min multiplied by THI minus TCI. So C min, as what we have found out, that is for the hot fluid, is 1889 multiplied by the temperature difference, 300 minus 35 for the hot fluid. Work it out, you get 5 times 10 to the power 5 watt. We could make use of the same relationship, very similar relationship. We want to find out what is that Q. And particularly, we are interested just to look at QC for the cold fluid, but you can also work it out to find the QH, since QC and QH are equal to each other. So I'll just choose one. And I tend to choose the one that is given instead of the one that I calculated. The reason is because I may calculate wrongly. Press that as 1000 and then that's it. I'm off the tangent. So QC is the one that those numbers will be provided. Your CC multiplied by TC naught minus TCI. Those are the numbers that are provided. So I'll make use of that. That will be 4197 multiplied by 125 minus 35 equal to 3.78 times 10 to the power 5 watt. So it's sort of like you could already see what is going to be your effectiveness. Effectiveness is equal to Q over Q max. So your Q over here, 3.78 times 10 to the power 5. Q max, 5 times 10 to the power 5. So it got to be a number that's between 0 and 1. So if you work it out, you get 0.755. This effectiveness number is sort of like more or less the kind of effectiveness you could expect from a heat exchanger. A heat exchanger is considered effective enough for heat exchanging work. So 0.755, around that region. I've seen 0.6 up to about 0.8, near to 0.9 sometimes, and those sort of heat exchanger effectiveness. So I'm going to make use of that CR. Okay. I'm not sure, should I put an R over here because Coleman don't say R, but Glasgow say R. Which one do you want? Coleman or Glasgow? Let's go with it. So, die-hard supporter. I'll let Coleman know about it. Okay, so maybe CR because, then when I pronounce it, you know which one I'm talking about. So we know that CR is equal to C min divided by C max. This kind of equation is not provided, right? Because it's super easy. C min divided by C max. So, all right, you do it. So that's equal to 188.9 divided by 4197. You get that number as 0.45. And the last thing that you need would be your NTU we represent it by just N, or writing the whole thing as NTU, equal to UA divided by C min. So what we're interested is to find out what is the NTU. Okay? And the way to figure it out is that you would have your CR and you would have your effectiveness. So now I want you to have a look. Which graph do you think you'll be using? 1, 2, 3, 4, 5, 6. Well, that's the only thing that you need to be tested. That you know which graph to go for. So it's the fifth one, this graph over here, because it says it's cross flow, both fluid are mixed. How do I know that? That's because over here both fluid are mixed. Okay. So I'm going to make use of that with this number, epsilon 0.755, and your CR that's 0.45. Let's have a look. Over here. Okay. So these lines are all your CR, and you have your epsilon over here. So epsilon was 0.755. This is 0.7 over here. 0.755 somewhere. It's going to be somewhere over here. Right? Epsilon equal to 0.755. So you could use your ruler, make that projection. Yeah, okay. And you have your CR at 0.45. This line over here is 0.25. This line over here is 0.5. So 0.45 is somewhat like over here, right? Near enough. I accept a certain margin of error, right? But if you have it over here, if you project over there, you are by yourself. Okay. So put it down. Actually, I know what is the NTU number, so I'm going to project it down. You get NTU value of 2. Some of you may get 2.2, 2.1. Again, my error margin says that yes, you are a hardworking student. Okay, take that. So I'm going to take that value 2, equate this equal to 2. So this is from the graph above. Okay. So I have the rest of this, so I'm going to express this A as my subject and move the others over to C min divided by U. There will be 2 times C min here. That was 4197 divided by U, which is the number that's given to you in the question. That will be 100. So work it out, you get that equal to 37.8 meters squared. Oh, C min, yeah? 1889. Is it right? Okay. So let's go for a quick break and then be back 5 minutes later, and then we'll look at your example 2.